A quick quiz question. I wouldn't really grade this quiz. It's just kind of off the wall at this point. But the problem's not too hard to understand. Okay. If you go 2 inches, okay, if you're walking on a hillside or something, if you go in this direction, you go 2 inches for every foot. You rise 2 inches for every foot. If you go in this direction, you rise 3 inches for every foot. Okay. So I didn't really write down the question. But question is, how quickly would you rise direction? That's not really well stated, but how many feet, how many inches per foot would you rise if you went in some direction? Okay. And this rectangle here is a little bit misleading. Okay. Let's just say you went in direction theta. Okay. You went in the direction that makes an angle theta with this horizontal direction. Then the question is, how far would you rise as you went from here to here? Okay. Let's say this arrow has, let's just say this is the unit vector. But let's just ask the same question. Think about it for a minute. How far would you rise if you went 1 unit along that unit vector? 1 foot along that unit vector, let's say. Okay, let me just make you, when we talk about this, talk about it a little more. I keep commenting that I'm not seeing many pictures in your work. Okay. I didn't get all the work last night. I think I got work from half the class. By the time I got to look at it, then I got one or two more. Okay, somebody still owe me. Maybe you don't, maybe you've turned it in, but I'm not going to send out my comments until I've got them all. Okay, so make sure you get them to me so everybody can have my comments. Okay, anyhow, you got a unit vector here, rising 2 inches per foot in this direction, rising 3 inches per foot in this direction. Along that unit vector, the horizontal displacement and vertical displacement are cosine theta and sine theta. These are your displacements. So cosine theta in horizontal direction, rise is 2 inches times cosine of theta. You go cosine theta feet. And I'm talking about horizontal direction and vertical direction on the board, not up or down the hill, right? So that's a little bit ambiguous. That's just 3 inches sine theta. Okay. Another question, what direction would you go if you wanted to go up as fast as you could? If you wanted to go up the hill as fast as you could? Would you go in this direction? Or would you go a little bit this way because you don't sacrifice much displacement in this direction, but you get a lot more, you get a lot of displacement in this direction. Does that make sense? Okay, because the cosine or the sine of this angle is going to stay very close to 1 until you get out there, 20 degrees or so from this direction, okay? And you're going to get a lot of cosine by going that 20 degrees. Your cosine is going to be at about 0.3 or 0.4, okay? And you're going to get 2 inches for every bit of cosine you have. You're still going to get most of your 3 inches because your sine hasn't changed much. Does that make sense? You should really think about that until it does, if it doesn't, okay? That's really foundational for understanding the variations you get due to trigonometric variations, okay? I don't have a good statement because it applies in so many contexts. Okay, well, anyhow, that's we're gonna cut through that to where you can calculate it easily. And if you haven't thought about it, you're not going to understand what you're calculating. Okay? So I really want you to think about this. It all comes down to this idea. Okay, so start making sense of this. The del operator is I partial with respect to x plus j partial with respect to y. Can you find del of x squared y cubed? Let's write it down, jot it down quickly. First thing you want to do, of course, is make it easy and replace del by this, okay? Then you probably want to use the distributive law. It'll apply here. These aren't really algebraic quantities, they're operators. You've probably seen operators in differential equations. So you should be kind of familiar with the idea of an operator. But for right now, just treat everything like an algebraic quantity and do what seems obvious. I think most of you have it, or up to maybe a calculation error or something. But let's make sure. Okay. You got to get I partial with respect to x plus j partial with respect to y of x squared y cubed. And then you treat this like a multiplication. Again, I partial with respect to x is part of an operator. It's not an algebraic quantity, but when you apply it to an algebraic expression, you do get an algebraic quantity. So if you can do the derivatives, these are really easy to calculate. Okay, partial respect of x squared plus y cubed is 2xy cubed. And now I'll put the I at the end. I wanted to put the I at the beginning up to this point so that you would see that the partial applies to the expression rather than having to kind of sort that out. But anyhow, it's going to be then 3x squared y squared j. Okay, makes sense? I better spell that, not leave letters out. That's called the gradient. Of f of xy equals x squared y cubed. I didn't use f of xy notation up here, but you're saying now that x squared y cubed is over f of xy. Can we write that as del f? And we read it as del f. And just to be explicit, for f of xy equals x squared y cubed, del f is 2xy squared plus 3x squared y squared, 2xy cubed I plus 3x squared y squared j. Okay? That gradient has some very significant properties. The magnitude of del f is the rate of maximum increase of f of xy. Okay? Just like there's some direction we could go here that would give us the rate of maximum increase on this hill, there's some angle theta that would maximize the total distance we go vertically on that hill. Okay? This maximizes this function at a given point. At different points, you'll have different rates. The direction of del F is the direction of maximum increase. The rate of increase in the direction of a unit vector u is, I'm going to give you the notation. I'm going to do a big D sub u and that's del F dot U. Del F is Fxi plus Fyj, which is just what I said here, except, we got the Fx when we took our partial derivative. If this is F, this is the x derivative of x times I, right? And this is the y derivative of x times j. Okay? So in terms of what we just saw, you will understand that del F comes down to just Fxi plus Fyj. I could have written it in that format, but then I wouldn't have been making you think through these partial derivatives in the same way. Okay? And I think you do better if you see it first that way. And very possibly there's too much glare on my computer screen. I can never tell. It's visible. Of course, I get this end of it. I don't get everything on that end, but that's all right. Okay. Del F is Fxi plus Fyj. So D sub U F, and I should have written D sub U of F here. Equals don't have room to write it. I'll write it this way, Fxi plus Fyj dotted with cosine theta I plus sine theta j. Because of course, any unit vector can be written as cosine theta I plus sine theta j, right? Remember that from earlier, one of the easier things you've done. Hopefully you haven't lost track of it because you're going to continue to need it. But yeah, this will refresh it. Okay? Where theta is the angle of the u vector relative to the positive x-axis. Not sure. We're still seeing everything. Okay? Well, to relate this to the question we started with, about going up 2 inches for every foot here, 3 inches for every foot there. Okay. If in the x direction you go up 2 inches for every foot, that means your x derivative is 2/12, right? The rate at which you're going up respect to distance over is 2 out of 12, 1 out of 6, okay? Or 3 out of 12, 1 out of 4 for the y direction. And we're going to put this in the context of z equals f of x, y. So can you calculate the direction of maximum increase and the rate of maximum increase? I don't think I really have to show you in the sense that you couldn't get it, but so you're almost there. And so I said, what's the rate of maximum increase? What's the direction of maximum increase, right? We got fx and fy. That's the I component, that's the j component. Just going to use the Pythagorean theorem. Okay. You'll get 1 over 36 plus 1 over 16. Okay. And you're going to make me add those fractions. Common denominator is got 4 in common. So you're going to multiply 9 by 4 is 36 by 444. Okay, so that's 1/36, which is 4 plus 9 over 144, which is the square root of 13 over 12. Approximately 3.6 something over 12. And I keep it over 12 just because that's handy, because that's how much you go up for every foot. Like 3.6 and 3.7 inches per foot. Okay? If I did my arithmetic right, and that makes pretty good sense, I'm pretty sure that's right. Don't think you get up to 3. It might round off to 3.7. Okay, well, that's a rate of maximum increase. .6 inches out of 12. What's the direction of the maximum increase? Well, what's the direction of fxi plus fyj? It's our tangent of fy over fx. Again, that should be pretty instant, the amount of trigonometry you've used. Okay. So be careful that you're not thinking punch this and punch that when you do your trigonometry. Think about the functions. Just don't get in the habit, here's what you punch when you do this. There's a tendency to do that. Just like AI dumbs people down if they rely on it. The way we've been teaching math, letting people do math, doesn't build the kind of insight that you're going to be happy that you have if you develop it, okay? Trigonometry should be pretty second nature to you, but depending how it's been taught, depending what you've actually been asked to do, and depending on your work habits. If you're not really thinking the trigonometric functions, or if you're just doing them kind of by reflex, make sure you understand them a little better. Okay. Now, I'm not going to tell you about that. I mean, I just said it's the arctangent of F1 over Fx, right? Which is going to be the arctangent of 1/4 over 1/6, which is the arctangent of 1.5, which is around 60 degrees or so. Okay. And that makes sense. It's closer to the 3-foot or 3-inch per foot direction than it is to the 2-inch per foot direction. By tilting out to somewhere around 60 degrees, you lose a little bit of that 3 feet, but you gain a good bit of that 2 feet. That's the way sine and cosine behave. Well, worth thinking about to make that intuitive rather than just a result you get out of a spreadsheet or a calculator, okay? It allows you to think about problems in a different way. It's not just symbolic. It's not just here's how you get the answer. There's the intuition with it. And build as much of both as you can. You need both. Okay? All right, well, that pretty much covers section 4.5 or 4.6 is. I don't know. I think it's 4.6. It's the one on directional derivative and the gradient. This d sub u thing is called the directional derivative in the direction of u. It's the rate of change in the direction of u. Okay, so let's go ahead and calculate a couple of those. Keeping it simple, if f of xy is if the gradient make it 0.8i plus 0.6j. Can you read that? 0.8i plus 0.6j. What angle does u make? 53 degrees. Cosine and sine of 53 degrees are 0.6 and 0.8. Okay? You see that a lot? I saw it a whole lot. Why? Because 37 and 53 degree angles are fairly typical angles, and you can write down the sines and cosines without having to have a calculator, which didn't exist 60 years ago. Okay? And it was a shortcut. We love to see those angles on tests because we didn't have to figure out square roots and stuff like that. Okay? Didn't have to go to tables. We still learned the trigonometry probably better than people are learning it now. And it's simple, very simple. You don't have a machine intermediating your thinking. Then when the machines come along, they're really easy to learn to use. You think first, then you learn how to use the machines. Now, it's not the way things are done right now, but kind of keep that perspective. It's useful. Okay, U is 0.8i plus 0.6j. And U equal 0.6i plus 0.8j. This is 53 degrees. You got more. I did it backwards. This is 37 degrees and this is 53 degrees. Yeah, back 60 years ago, people knew how to keep that straight. Okay. Not saying everything's better 53 years ago, but there's something to be learned from the way technology has kind of invaded our thinking. And you want to be aware of it with AI. So I talk about it. Okay. It's not a good old days type thing. A lot of advantages now, but people aren't taking advantage of them. 37 degrees, 53 degrees. Meaning this has more horizontal and this one has more vertical. So you're going to get a bigger result here than you're going to get here. So I'll give you just a minute or so to write out at least one of those. Then I'll write them out for you. Look, we're still recording. Did I not turn that off? I didn't. Hope I was recording before. Anyhow, question is, if del F is 1/6 I plus 1/4 J, what is DUF for U equal 0.8 I plus 0.6 J, which corresponds to 37-degree angle above the x-axis, or for U equal 0.6 I plus 8.8 J, which is a 53-degree angle. You would think that this one's going to come out bigger because you have more of the upward or the vertical direction in the plane, which is going to give you a steeper ascent, okay? As this does correspond to the problem we started with, okay? So D instead of writing out the letter U, I'll use point A, 0.8I plus 0.6J of F equals 1/6I plus 1/4 J dotted with 0.8I, 0.6J, which equals, oh boy, 1/6 of 0.8 is 4/3 of 1/10, which is like 0.133. And that's like 0.15 equals 0.283. Now, does that make sense? It's a little less than a third. That would correspond to a little less than 3 inches per foot. Okay, if I did that right. Okay. So 0.283. That might be a little high. Something might be wrong. That should be 1.5. That should be 1.3. Yeah, I'm going to take it. Let's just try this one. D in the direction 0.6I plus 0.8J F is going to equal okay. Uh, believe that one comes out 0.1 plus 0.2 equals 0.3. Now, what this illustrates again, what you want to understand is here's your direction for 2 inches per foot. You come up to 37 degrees and you go in this direction. So you don't quite get all 2 inches per foot, but you get a good part of that point above that 3 inches. Okay. And it gives you a slope of 0.283, a rate of 0.283. I'm still suspicious of that, so work it out yourself. But okay. Now you come up even higher to about a 53-degree angle, and you're getting a lot more of that 3 inches, and you're still getting a good bit of the 2 inches per foot. Okay. So you're getting slope of 0.3. Okay. And that corresponds to, I think, probably 3 inches per foot. Just, well, retort, I'm losing track of my assumptions here. Anyhow, as expected, the directional derivative increases. The directional derivative is how much change in whatever per unit of distance in that direction. Okay. Going to shift gears. These are all basically simple calculations. Make sure you really pay attention to what they mean. Don't be content to just punch buttons. I think I've already said it today. I'm not seeing many pictures in your homework, which makes me think you're taking the expedient way, which might be your only choice given the stresses of your curriculum. But it's not the way to maximize your knowledge. So try to do at least a little bit of sketching. The more the better. Things stick better if you sketch them. And it might not be true for you. It's not true for everybody, but it's true for most people. And use this base now to talk about maximum and minimum of a function of two variables. Now, you know, to do the maximum and minimum of a function of one variable, you find the critical points, then test them, right? So for any max min, first idea to find relative maximum and minimum is you find the critical points and test them. For f of x, y, critical points are where your first partial derivatives are zero. Okay? It means in 3 dimensions, at a given point here, let's just say this point, if we cut the function by a plane parallel to the YZ plane, the function's going to maybe look like this, and maybe this will be a critical point for your fx is zero. I'm not seeing these kinds of pictures. You really ought to learn to draw these pictures. Okay? Does that make sense? I've drawn the pictures. I know you've thought about them. You've seen similar pictures in your text where things are cut. Okay? They're not nearly as good as mine, but they're okay. So nothing's as good as what you can construct. Nothing's as good as what you can sketch. Okay, so you'd have fx equals zero. That's great. Okay, now let's cut it with a plane parallel to the xz plane. And we come up here and we just take a point here, a point here. Comes up here, comes down here, and does this. And now you have a slope in the y direction. This little segment indicates the tangent line in the x direction. This indicates a tangent line in the y direction. Fy is not equal to zero. Oh, you know what I wrote it wrong. Picture's okay, labeling, careless. This is Fy. This would be Fx. X is changing along this side. Okay. Not a great picture, but it's possible if there are points where Fx is zero or Fy is zero, where it's horizontal. If you cut the plane or cut the graph in this direction, and Fx isn't, it's perfectly normal for that to happen. If they're both zero, then you might have, well, you've got a critical point. It might correspond to maximum or minimum. It might also correspond to a saddle point. where one function is doing this at this point here, and the other function is doing this. Okay, so it's like this. There's your peak. It's a valley if you cut it in this direction. I'm not going to attempt to draw that saddle point. So kind of, you know, I can draw it so that I can see it. I'm not sure I can draw it so that you can see it. Look at the pictures in the book. Well, you have a test. It's all very analogous to what you do with maximum and minimum of one variable, which had better review if it's not totally clear to you right now. Okay. At a critical point, you test the discriminant, which is and that's wrong. FXX plus FYY minus FXY squared. On the surface, this indicates a curvature, FXX being positive means what? Means that your slope is increasing, right? Second derivative of a function being positive means it's concave up. Means it has a minimum. Okay? And FXX negative. I had a plus there. That just wasn't thinking. Okay. If FXX and FYY both have the same sign, that means it's concave in the same way here as it is in this direction. It's concave up in the X direction, concave up in the Y direction, which means you have a minimum. Unless this thing gets in the way. Okay? We'll talk about that in a minute. So your first expectation would be XX and FYY are both positive. You got a minimum. But you still might have a saddle point because you don't know what's going on in the 45-degree directions. If they're both negative, then you figure you have a maximum. They're both concave down. So unless you got a saddle point, you're okay. Your test is that this has to be, now if this is greater than 0, then you have a maximum or a minimum, depending on the common sign of FXX and FYY. If FXX and FYY have opposite signs, that means in one direction you have concave down, in the other direction you have concave up, and there's your saddle point. And it doesn't matter what FXY is. Okay? If these have different signs, this is going to be negative, and whatever this is, you're still going to be negative. You're not going to be greater than 0. Okay? So that test gives you a maximum or minimum. also, okay, because if it's negative, then these have different signs. What if this thing is equal to zero? That can happen. It tells you nothing, and you better figure out something else, depending on the situation. We're not going to worry too much about that. You're probably going to encounter it. Talked about it if you do. Okay? That's basically it for relative maximum and minimum. Okay? It's real easy. I could explain more about the reason for it. And I don't think I can do that in the 10 minutes we have. Some other stuff we need to talk a little bit about. One being, these are relative maximum. That means the highest point in some neighborhood of itself or the lowest point. You also can have boundaries, and you know from what you did in first year calculus, if you have a function defined on an interval, you have to check the endpoints of the interval to see if your maximum or minimum occurs at an endpoint, right? That's your global maximum or minimum. So function one variable, check all your endpoints. In other words, you could have a function that looks like this. I did it wrong. Okay, you have a relative max here. And a relative min about here. Your global max occurs at this endpoint. Your global min occurs at this point because the global max is higher than any of your relative maxes, and your global min is lower than any of your relative min. Okay, so you've always got to check the inputs if you have a finite interval. Now, function of two variables. Again, you got to check all boundaries. Just an example of what it might look like if you have a bounded f of xy equal x squared minus y squared plus 2y plus 6. On the unit circle. Circle radius 1 centered at the origin. Okay. Now you can check fxx is 2x, is 2, I mean. fyy is 2 times 1 minus y. You can check that out. You have a critical point when fxx and fyy are both 0. So x equals 0, y equals 1. You just set each of these equal to 0. Oh, wait a minute, stop. It's not fxx, that's fx. Okay. fxx is 2, fyy is negative 2. fxy is 0. Just so this thing is less than 0. And what's that mean? Means you got a saddle point. Okay. Hit the point 0, 1, and then plug in 0 and 1 here. You get 0, 1, 8. Okay. So any global max on the unit circle has to be on the boundary. Well, on the boundary of the unit circle, you go to cosine theta and sine theta, parameterize it. That'd be a good thing to do, but I don't want to get Don't want to do that right now. We're going to do plenty of parameterization over the next few weeks. Okay? X squared equals 1 minus y squared. Y comes down to a function of a single variable. 1 minus y squared plus 2y plus 6 equals 1 minus 2y squared plus 2y plus 6. It's a function of one variable. The derivative is negative 4y plus 2. Looks like you got a critical point at y equals 1/2. And then your second derivative is going to be negative 4, which means it's concave down, so that's going to be a max. So whatever this function looks like, here in a circle, but if you want to do it now in 3 dimensions, what's this thing look like as you go around the unit circle? Apparently for y equal 1/2, if I did this correctly, that's where the graph is highest. So we'd have a point like here and a point like here. And then you could analyze the graph of this thing. It's simply a quadratic function. Okay. But it's going to have its maximum here and here. I'm not going to attempt to draw it right now. I mean, I'll just do it real quick. You got minus 2y squared plus 2y plus 7 equals 0. Your axis of symmetry for this would be that y equals 1/2. Okay? Axis of symmetry is like your quadratic formula. You got negative b plus or minus the discriminant, square root of the discriminant over 2a. Just take the minus b over 2a, and that's halfway between your zeros, right? Probably carry around with you, because then you could take the negative b over 2a. You know that that's the axis of symmetry. And b is 2, a is negative 2. Negative b over 2a is 1/2, which coincides with this. And that also coincides with the vertex of a quadratic function. So this thing's going to have 2 branches. It's going to be 0. This means this number is much bigger than 1, or much less than negative 1. It's not within the domain of numbers on the unit circle. It means the zeros of the function don't occur on the unit circle, which is not surprising because you got that plus 6 there and the x's and y's aren't that big. Make sense? Think about it. Okay. Yeah, we're a little over time, sorry. But that's kind of what it looks like when you're looking at a boundary. Different boundaries give you different geometries. One more comment. I am gonna put a test in the testing center. Tomorrow or Thursday at the latest. Won't be due until the week we get back.
And that's on chapters 1 through 4.5.